This paper is on handling bidirectional control flow. I am Yizhou Zhang at the University of Waterloo, and this is joint work with Guido Salvaneschi and Andrew Myers. Software is becoming increasingly asynchronous and event-driven. As a result, programming languages are racing to add support for advanced control flow patterns. This trend is witnessed, for example, by the flurry of control flow features added to JavaScript in recent years. A closer look at the more advanced language features shows that they all address control flow patterns involving more than one control effect. That is, control flow is bidirectional. For example, client code can issue async await to request the runtime to run computations asynchronously. But when that computation raises an exception, the runtime will transfer control back to the client so that the client code can handle the exception. There is also language support for other bidirectional control flow patterns. These language features simplify control flow programming because they enable programmers to avoid callback-based spaghetti code, which is difficult to write and to read. However, there are issues with this approach to language design. First, language features are added in an ad hoc way to support particular control flow patterns. It would be desirable to have a unifying language abstraction that could subsume all the control flow patterns once and for all, especially the more complex bidirectional ones. The second issue, and perhaps the bigger one, is that there is not enough static checking of control effects to guide the programmer in reasoning about the control flow. For example, in languages supporting async await, unhandled asynchronously raised exceptions are a common source of bugs. The consequence is that programming remains error-prone. This work addresses these issues. We introduce a unifying language abstraction capable of expressing the bidirectional control flow patterns. We also provide a type system for this language abstraction and show that type system statically rules out unhandled effects and accidentally handled effects. This new language abstraction generalizes the idea of algebraic effects, which are already a unifying language abstraction for expressing individual control effects. To provide background, the unifying power of algebraic effects comes from the ability to define signatures for effects. For example, this slide shows an effect signature called yield. This signature contains one effect operation. Using this yield effect, we can define a generator for linked lists in a declarative way. We yield the head of the list, and we recursively iterate the tail of the list. Because we invoke the effect operation, static checking of effects requires us to put the yield effect in the method header. The client code then needs to handle this effect by providing an implementation for each effect operation in the effect signature. Here, the handler prints the yielded integer and resumes iteration. Invoking an effect operation raises an effect. When the yield effect is raised, the runtime transfers control to the handler in the client code, which prints the yielded integer. After printing is done, control is resumed at the invocation of the effect operation, so that the generator will continue to traverse the rest of the list. Now consider the programming challenge of providing an iterator abstraction that allows client code to imperatively modify the list during iteration. That is, we want to allow client code to interrupt the iterator to request the list element to be replaced by a new value. To address this need for bidirectional control flow, we propose a simple generalization of algebraic facts. We allow effect operations to raise further effects. In this example, we define a new effect called replace, and declare operation yield has the effect replace. So we call yield an effectful effect. Because yield is now declared to be effectful, we are authorized by the type system to call replace in the yield handler. In this example, we replace all negative integers with their opposites. Invoking replace in yield causes control to transfer to the invocation side of yield. The invocation side of yield is the iterator, which handles replace. In fact, the type system requires the iterator to handle replace. This replace handler modifies the head of the list using the new value provided by the client code. After replacement is done, control will resume at the invocation side of replace, and the client code will continue to do the printing. To summarize, effectful effects enable dynamically transferring control to and fro between program fragments. In the meantime, static checking of effects guarantees that all effects are handled, regardless of their directions. Allowing effect operations to have effects makes them appear like methods. Ordinary method calls like iterate and print naturally go down the stack. Raising an effect like yield can be viewed as a method call that goes up the stack. But then we can attach effects to these methods too. So raising an effect like replace becomes a method call that goes back down the stack. And we can go as far as we want with this. This observation suggests that there is really no essential difference between raising an effect and calling a method. And we should be able to unify algebraic facts with interface-based object-oriented programming. In fact, under this unification, yield and replace are interfaces. And the handlers for these effects are of a special kind of objects whose lifetimes are stack-bound. Moreover, just as objects can refer to themselves via a special this or self variable, generalized effect handlers can use themselves to handle their own effects. There are many possibilities with effectful effects. We can have iterators that support not only concurrent replacement, but also concurrent removal. Another possibility is the so-called async generators, as found in recent editions of JavaScript and Python. Async generators are useful for iterating over data sources that produce data asynchronously. With effectful effects, the iterator invokes an async operation to schedule a high latency computation to be run in the event loop, and yields a promise to the client. When the client awaits that promise, control is transferred back to the client, and further to the event loop, either to retrieve the result of the finished computation, or to stand by until the result is ready. A third possibility is async await with exceptions. It's not uncommon that high latency computations running in the event loop can raise exceptions. When such exceptions do arise, the reasonable thing to do is to propagate them back to the client code when the client code awaits the result of the asynchronous computation. This can be achieved simply by attaching an exception effect to the await operation. Importantly, the type system guarantees that the client code is prepared to handle these asynchronously raised exceptions. Finally, combining all of the previous scenarios, we can have an iterator that schedules asynchronous computations and yields promises, which when awaited can raise exceptions to be handled by the iterator. The underlying control flow is complex, but still remains manageable because static checking of effects provides guidance on where to apply effect handling. We can also view the signatures of effectful effects to be choreographing communication between two processes. In the iterator example, the signatures specify a communication protocol between a client process and an iterator process, in which the client can respond to a yield with a replace. We can also have recursive signatures that specify recursive communication protocols. For example, ping-pong are a pair of mutually recursive effects. They specify a protocol in which two processes send messages to each other in lockstep. Usually, effect handlers are dynamically scoped, meaning that upon the raising of an effect, a handler is found by climbing up the call chain and finding the first handler with a matching signature. Dynamically scoped handlers are known to cause accidental handling. The reason is that inside the implementation of an effect polymorphic abstraction, a dynamically scoped handler can inspect the runtime instantiation of the polymorphic effect, which ought to be transparent to the handler no matter how it is instantiated at runtime. This ability to dynamically inspect can cause handlers to intercept effects they are not designed to handle. It leaks the implementation detail that the effect polymorphic abstraction handles certain effects within its implementation. It's not hard to imagine that a bidirectional control flow would further muddle the problem. In particular, dynamically scoped handlers in handler resumptions could handle reverse direction effects by accident. Prior work has proposed to use lexically scoped, lifetime-bounded handlers to prevent accidental handling. This fix generalizes naturally to effectful effects, since handlers are viewed as lexically scoped, stack-bound objects. We formalize lexically scoped, stack-bound effectful effect handlers together with a unification between effects and objects. We prove a standard type safety theorem, which says no effects go unhandled. But soundness here means more than type safety, so we aim for an abstraction safety theorem that implies no effects can be accidentally handled. This theorem is parametricity, which says expressions behave the same irrespective of how polymorphic effects are instantiated at runtime. So reasoning about control flow is truly compositional. And the proofs of these theorems are mechanized using the clock-proof assistant. To conclude, we have provided a language design recipe that addresses a variety of programming challenges involving bidirectional control flow. We have also established formal guarantees that underpin programmers' compositional reasoning about bidirectional control flow. We hope these contributions will help identify a feasible path toward unifying and integrating advanced control flow mechanisms in mainstream programming languages.